Let's solve yet another thermodynamics process problem that takes place in a closed system. A closed rigid tank is filled with water. Initially, it's at the critical point. The water is cooled until it attains a temperature of 400 degrees Fahrenheit. For the water, show the process on a sketch of the TV diagram and determine the heat transfer in BTUs per pound mass of water. So let's lay out our storyboard. Got a schematic. I've drawn a rigid tank showing positive heat transfer going into the tank. The tank's filled with water, and I'm drawing my system boundary around all of the water molecules. So the water is our system. We know that process 1-2 is a cooling process, and we're given some data. At state 1, we know the temperature and pressure are the temperature and pressure of the critical point. And we know state 2 is 400 degrees Fahrenheit. So how do we get critical point data? Let's look at a TV diagram. So let's draw our vapor dome. Okay. And the critical point is the top of the vapor dome. So the left side of the vapor dome, this is the saturated liquid line. And the right side of the vapor dome is the saturated vapor line. And they run headlong into each other right at the top, and that's where both lines end. And in the table, we have data showing properties on the saturated liquid line. And we have another column showing properties on the saturated vapor line. So where these two lines end is at the critical point. So if we want to know the temperature and pressure at the critical point, we would go to the very last row in the saturation table, and that is going to be the critical point. So the temperature at state 1 is the temperature of the critical point, and the last line in the saturation table shows that temperature to be 705.4 degrees Fahrenheit. And again, the last line in the saturation table shows that the saturation pressure at the critical point is 3204 psi. And of course, state 2 was given as 400 degrees Fahrenheit. Now, if we start at state 1, the critical point, and cool it at constant volume, I mean, the tank is rigid, so it has a constant volume, and it's a closed system, so there's constant mass, so it's constant specific volume. So that means we're going to drop straight down on a vertical line from the critical point down to 400 degrees Fahrenheit. Right? Clearly, state 2 is going to be a saturated mixture. So we're going to model this as a closed system. We're going to ignore any changes in kinetic and potential energy. And it's a constant volume or a constant specific volume process. And we want to find the heat transfer that takes place during this process in BTUs per pound mass. And that's actually Q over M, so heat transfer per unit mass, which instead of writing capital Q over M, we often just write that as a small q, which indicates that it's per unit mass. So let's start with an energy balance for our closed system. We can see that the change in energy is delta U plus delta KE plus delta PE, and that's also equal to Q minus W. Now, previously in our model, we said that delta KE and delta PE would be taken as 0. And a rigid tank has no mechanism for doing work, so work also has to be 0. That leaves us with just delta U is equal to Q. Well, I can rewrite that as Q is U2 minus U1, that's capital U's, which are have units of energy. And that's equal to the mass times the change in specific internal energy. So we can say that Q over M, which we often just write as a small q, is just the change in specific internal energy. Let's find U and V for state 1. And again, from the saturation table, we'll go to the last point in the table, which is the critical point. And we grab the values out of the table. We see that U1 is 872.6 BTUs per pound mass, and V1 is 0.05053 cubic feet per pound mass. Now let's find some values for state 2. We want to find U and V values, and we're going to just get the specific volume of a saturated liquid and the specific volume of a saturated vapor, and we'll get the internal energy of the saturated liquid and the internal energy of the saturated vapor. So all of these values are taken from the saturation table at 400 degrees Fahrenheit. And we also note that at the second state, the saturation pressure is 247.1 psi. So we can now determine the quality of the state by observing that this is a constant volume process, and therefore the specific volume at state 2 is equal to the specific volume at state 1, which we determined to be 0.05053. So the quality is simply V2 minus V sub F over V sub G minus V sub F, all values taken at state 2, which we remove these values from the table. And I get that the quality at state 2 is 0.0173 or 1.73%. Well, now that the quality is known, we can find the internal energy of this saturated mixture. U2 is just U sub F plus the quality times U sub G minus U sub F, all of these values taken at state 2. We have all of these previously described, and we find that the internal energy at state 2 is 387.1 BTUs per pound mass. Now we can find the heat transfer Q. It's just the change in the specific internal energy, or U2 minus U1. Well, we have those values, and we see that Q calculates to be negative 485.5 BTUs per pound mass. And of course, Q is defined as positive when we're adding energy to our system via heat transfer. So the negative sign indicates that we're removing energy via heat transfer, which is to say we are cooling the system.